So we are discussing about the root locus problem, second part of our problem. Now we have find out whether any breakaway or breaking points existing in the system. So we got that the given problem, the root locus has neither breakaway or nor breaking points. So here we can check that the next step is to find the angle of departure and angle of arrival. So that is the next step, to find the angle of departure or angle of arrival. Here we can see that there are two complex poles. So if there are two complex poles, that means there will be angle of departure. If there are two complex zeros, there will be angle of arrival. The angle of departure and angle of arrival is associated with complex poles and zeros. So complex poles means the angle will be angle of departure, because from poles the root locus branch is going. The starting point of the root locus branch is pole, and from pole it is going. But when complex zeros are there, we know that the root locus branch is ending or terminates at zeros. So the arrival angle of root locus branch will be considered when you have complex zeros. But here in this case we have complex poles. So we have to find out the angle of departure. The angle of departure means the root locus branches starting from the complex poles that will start from some angle. So that angle is known as angle of departure. So in order to find out the angle of departure, what we have to do is we have to plot, we have to consider any one of the complex poles. So now I am considering this pole as my first complex pole, that is corresponding to this quadrant, that is -2 plus j3. So I am considering this as my first pole. So to this point or to this pole, we have to plot straight lines from all poles and zeros. Okay. So we have to plot the straight lines from all poles and zeros, open loop poles and zeros, to a complex pole. So we can consider any of the complex pole. Here you can see that there are two poles. So I am considering this pole. Okay. So from all other poles and zeros, we can draw straight lines from all other poles and zeros. Okay. So now there are total 3 poles. So to this pole, that is marked at A, there will be a straight line from the pole S is equal to 0, and another straight line from the pole S is equal to -2 minus j3. Now what is the equation to find angle of departure and angle of arrival? In order to find angle of departure is, the equation to find angle of departure is 180 degree minus sum of angles of vectors to the complex pole A from other poles. That is, this is our complex pole. So sum of angles of vectors to the complex pole A from other poles, all other poles, അതായത് ബാക്കിയുള്ള എല്ലാ പോൾസിൽ നിന്നുള്ള ആംഗിൾ, വെക്ടേഴ്സ് ഓഫ് ആംഗിൾസ് നമ്മൾ കൺസിഡർ ചെയ്യാം, മൈനസ് സം ഓഫ് ആംഗിൾസ് ഓഫ് വെക്ടേഴ്സ് ടു ദ കോംപ്ലക്സ് പോൾ എ ഫ്രം സീറോസ്. ബട്ട് ഹിയർ യു ക്യാൻ സീ ദാറ്റ് ദർ ആർ നോ ഓപ്പൺ ലൂപ്പ് സീറോസ്. അതുകൊണ്ട് നമ്മൾ ആ ലാസ്റ്റ് ടേം വി ഡോണ്ട് ഹാവ് ടു കൺസിഡർ, വി ഓൺലി ഹാവ് ഓപ്പൺ ലൂപ്പ് പോൾസ്. അപ്പോൾ നമ്മൾ എന്ത് ചെയ്യണം? വി ഹാവ് ടു ഡ്രോ സ്ട്രെയിറ്റ് ലൈൻസ് സ്റ്റാർട്ടിംഗ് ഫ്രം S is equal to 0 and S is equal to -2 plus j3 in order to this complex pole A. Now mark the angles of vectors, that is we can mark the angles of vectors as, the first angle is theta 1. Theta 1 is this angle. What is this angle? This straight line, you can see that this straight line, that is the vector from s is equal to 0 to the complex pole A. Okay. So, from s is equal to 0 to the complex pole A, this straight line makes with the horizontal axis or horizontal line. So, this is marked as theta 1. Now, other one is the other pole, that is at other complex pole -2 minus j3, that makes with the horizontal axis, that we can mark as theta 2. So, in order to find the angle of departure, we have to measure this theta 1 and theta 2. Using the protractor, you can measure theta 1 and theta 2. You can see that this is 90 degree. Okay. You can see that this is 90 degree. You can measure this theta 1 using the protractor. So, if you measure that, you will get theta 1 equal to 123 approximately and theta 2 equal to 90 degree. So, in order to find angle of departure is 180 minus sum of angles of vectors from all other poles, that is 123 plus 90 degree, plus sum of angles of vectors from all zeros. Here there are no open loop zeros, so we do not have to consider that term. So, the answer will be 180 degree minus 123.7 plus 90 degree. So, that is equal to 213 degree, that is minus 33 degree. Okay. So, the angle of departure corresponding to the complex pole A is minus 33 degree. Complex pole A corresponding to the complex pole A is minus 33 degree. Now, if we have two complex poles A and A complement, okay, we can write it as A and A complement, that are two complex poles. I can give that this as A star. Okay, A star. So, if there are two complex poles, we already find out the angle of departure corresponding to the complex pole A, that is minus 33 degree. So, no need to find the angle of departure of complex pole A star, because the angle of departure of complex pole A star equal to minus of minus 33. So, when we got the angle of departure corresponding to one pole, the angle of departure corresponding to the other pole will be minus of the angle of departure. So, it can taken it as, we can take it as plus 33 degree. Okay. So, these are our angle of arrival and angle of departure. Now, we can draw the angle of arrival and angle of we can draw the angle of departure corresponding to these two complex poles. So, we have corresponding to this complex pole, that is A, we have angle of departure is minus 33 degree. So, corresponding to this point A, okay, mark the angle here because it is minus 33, okay, minus 33 degree, and draw a straight line from this point A. Draw a straight line from this point A. Draw a straight line, okay. Now mark the angle as minus 33 degree. Now from this point, that is from the complex pole A complement, from the complex pole A complement, mark plus 33 degree. So you can mark from the protractor here in this point, mark plus 33 degree. This is plus 33 degree. Now we can draw a straight line corresponding to that point, okay. So this is plus 33 degree and this is a straight line corresponding to that point. So corresponding to the complex pole A, the angle of departure is minus 33. Corresponding to the complex pole A complement, the angle of departure is plus 33. So we have plot two angle of departures here. Now the next step is, we know that there are two root locus branches that are starting from pole A and A complement, and there are no breakaway and break-in points. So the pole starting from here should start with respect to this break angle of departures, and it should go to infinity, to the 0 at infinity, asymptotically through these asymptotes. So asymptotically means when we drawing asymptotes corresponding to, when we drawing the root locus corresponding to these asymptotes, the root locus should never cross the asymptotes. That is the condition. The root locus should never cross the asymptotes. It will goes to the 0 at infinity asymptotically. That is our assumption. So the next step is, we know that the root locus branch that starts from here and it is going to the to 0 at infinity through this asymptotes, and it is going to infinity through, or it is going to infinity asymptotically, and we can see that the root locus branch will cross the j omega axis. Here also, in this problem also, the root locus branch will cross the j omega axis. So what we have to find? We have to find the crossing point with respect to the imaginary axis. So in order to find the crossing point with respect to the imaginary axis, we have to write the characteristic equation of the given system. So that is s cube plus 4a square plus 13s plus k equal to 0. Now s is equal to j omega. Substitute for s is equal to j omega. The equation will be j omega cube plus 4 into j omega square plus 13 j omega plus k equal to 0. Now we can rewrite this equation as j cube is equal to minus j omega cube. J square is minus 1, so it will be minus 4 omega square plus 13 j omega plus k equal to 0. Now we have to separate the real part and imaginary part. On separating the real part, on separating the imaginary part, we can write minus j omega cube plus 13 j omega equal to 0. So we will get the answer as omega square equal to 13 and omega equal to root 13, that is plus or minus root 13, that is plus or minus 3.6. So what is the crossing point with respect to j omega axis? the crossing point with respect to j omega axis. Here we have omega equal to plus or minus 3.6. Okay, we have got the omega value as plus or minus 3.6. So the crossing point of j omega axis is j omega equal to plus or minus j 3.6. This is the crossing point. This is the crossing point with respect to imaginary axis. With respect to imaginary axis. Now, so we have got the crossing point as here 3.6. We have got the crossing point here. You can see that. Okay. So these are our crossing point, plus 3.6 and minus 3.6, minus j 3.6 and plus j 3.6. So these are approximately the crossing points. Now the next step is we have to find the limiting value of k, that is at what value of k the root locus crosses the imaginary axis. So why are we finding that? Because we are plotting the root locus with respect to the value of k starting from 0 to infinity. That means at some point of k, this here we got that the the root locus crosses the imaginary axis. So after that value of k, the system will get unstable. Because why it is that? Because after that value of k, our root locus will move to the right hand side of S plane and the system will be unstable. When the root locus move to the right hand side of S plane means there will be, in the closed loop system, there will be poles on right hand side. So we have to find the limiting value of k, or the value of k for which the system is stable. So that limiting value is the value of k when the root locus meets the imaginary axis. So in order to find the value of k, find value of k corresponding to j omega or imaginary axis. So because that value of k is the limiting value of k, above that value of k the system will gets to unstable. So in order to find that, we have to take the real part of that equation. We have got minus j omega cube minus 4 omega square plus 13 j omega plus k is equal to 0. Now on equating imaginary part, we got omega value is equal to plus or minus 3.6. So in order to find that, we have to write the real part of the characteristic equation, that is minus 4 omega square plus k equal to 0, where k equal to 4 omega square, that is 4 into omega square is 13. So the value of k is 52. So this is the limiting value of k, above which the system will get unstable, or we can say that in order to the system to be stable, the value of k should be less than 52. For the given system is stable, to be stable, the value of k should be less than 52. Okay. So we have got that also, and we have got the meeting points. So how can we draw the root locus now? So for that, we don't have any breakaway or break-in points. So we have to start the root locus from this complex pole A and A complement through the angle of departure. Okay, through the angle of departure we have to start. So you can see that I am starting this through the angle of departure, and after some point the root locus should be asymptotically goes to infinity. This should asymptotically go to infinity. So, this is our root locus here. So, when you plot it from a complement, it should be like this, that is, it starts from the a complement through the angle of departure, that is at plus 33 degree, and from that it should asymptotically goes to infinity, and the meeting point of the root locus is minus 3.6j here. So, this is the root locus, that is starting from a complement. You can see that these are the root locus. This is meeting at the imaginary axis and it asymptotically goes to infinity, and here also it coming starting from a complement through the angle of departure, and after some point it has to go asymptotically to infinity, and the meeting point with respect to the real axis is minus 3.6j. So, these are the portions marked in red, these are our root locus branches. Okay. These are our root locus branches. So, we got that there are 3 root locus branches. Each root locus branch starting from the pole, it is ending at the 0 at infinity. Okay. There are no breakaway or break-in points. Since there are complex poles, there is an angle of departure that we got as minus 33 degree and plus 33 degree, and angle of asymptotes are also there, and centroid is, we got centroid as minus 1.33. The point of intersection of asymptotes, that is centroid, that is minus 1.33. Now, the meeting point of root locus with respect to j omega axis is plus j 3.6 and minus j 3.6, and the limiting value of k is 52. Above the value of k is when greater than 52, the system will be unstable because the root locus will move to RHS. When the root locus move to RHS means that the closed loop system characteristic equation or the characteristic equation of the system is having roots on RHS. So, above 52 the system will get unstable. Thank you.